In this video, we will be covering topics from week 2 of ENGG 201. We will be discussing equilibrium states, different kinds of systems, degrees of freedom, as well as discussing PT and PV diagrams, how to read them and how to interpret them. So the first thing we're going to be talking about is equilibrium states. So when you are given a problem, there are some main variables that you want to look out for. So we have things you already know, so that's mass, moles, volume, pressure, and energy. Some new ones that you may not have heard of before are density, specific volume, and molar volume. Some equations that you need to know. For density, density's units are kilograms per meters cubed. And we represent this with Greek letter rho. Specific volume is meters cubed per kilogram, which is represented by a V, and molar volume, which we denote with a V with the subscript M, and this is volume per mole. Furthermore, it's important to note that you can relate density and specific volume, where 1 over rho is equal to our specific volume, and vice versa is equal to rho. And this just comes from our units. If you see our units, it's basically just the reciprocal of one another. And molar volume you can find from getting the volume of your container and the number of moles present. Okay, so let's talk about different kinds of systems. In a non-reactive system, actually no, I'll talk about that afterwards. First, I want to talk about phases and components. So most of you probably understand that phases are things such as liquids, gases, solids, and vapors. But what are components? Well, it will depend on the kind of system that you have. So if we have a non-reactive system, that means we are not reacting to produce new species. So this would be things like water and salt, for example. So not creating new species. So in this case, we would have two components, which would be considering each separate species. So in this case would be water and salt. In the case of us having a reactive system, say if we had species that were all interacting with each other to produce new things. So then if we had ammonia, water, oxygen, and nitrogen gas, in this case, we would have 3 components, because rather than taking a look at each separate species present, we look at each element present. So each element present. So you see that we'll have hydrogen from our ammonia and water. So then we have hydrogen, oxygen, and nitrogen present. So in that case, we would have 3 components. Okay, so building off of that slide, let's talk about intensive and extensive variables. So the definition for intensive variables they are variables of a system that are independent of size. So these values could be things like ratio-based ones, like specific volume, molar volume, and density. Because say if you took a sponge and you broke off a piece of that sponge is still going to be made of the same material, so you can equate that to its density. So it's still going to have the same properties. And you could also think about that for specific volume and molar volume, because if you have a smaller piece, you'll have the same ratio of stuff per whatever when you break it off into a smaller piece. This could also include things like temperature, as well as pressure. Because again, pressure is newtons per meter squared. So if you have a smaller area or a larger area, it's still going to be proportional. And temperature is because it's evenly distributed throughout. So if you had a glass of hot water and you poured half the glass into another glass of hot water, it's still going to have the same temperature. It's not going to be cooler. It might be cooler by a little bit, but overall it would have the same temperature and properties. Okay, and then we have extensive variables, which is the opposite. So extensive variables are variables of a system that are dependent on size. So this would include things like size and volume, as well as mass. So if you took a cookie, for example, and you split it in half, each piece is going to have different mass, different volume, and different size. So these are things that are dependent on the size of a system. All right, so now let's talk about degrees of freedom. So degrees of freedom is an equation that we use where degrees of freedom is denoted as F. C is our components, plus 2 minus number of phases in a system. So degrees of freedom is the number of intensive variables in a system that can be changed. So if you had 2 degrees of freedom, for example, that means you could change things like pressure and temperature So you have two options to change two variables while one stays fixed. So the maximum you can have maximum degrees of freedom is 3, right? So if you can change all 3 properties, that means you have the largest range you can. And on the other hand, if you have, so minimum can be 0. So if you have 0 degrees of freedom, that means all variables are fixed. So you can't change anything in a system. So we'll bring this up again in our next slide, and it'll start to make a little more sense for you. So that's why it's important to consider the amount of components and the amount of phases that you might have in a system. Okay, so we are going to talk about pressure and temperature diagrams. Pressure and temperature diagrams are a plot of pressure. Actually, no, it doesn't really matter what units. Pressure and temp, where pressure is respondent of temperature. So this is like saying in our x-axis we have our temperature and we have pressure in our y-axis. So this is a graph to help us see properties of single component. So single component means that it's a pure substance. We're only dealing with the property of one thing of matter. So for example, you couldn't use it for water and salt or a combination of things. It would just only be for water or only for salt, for example. Okay, so there's a couple things to talk about. We have a few different regions here. I'm going to highlight them. So everything on this, in this green shaded region, is a solid at a specific temperature and pressure. This is solid right here. And everything in this yellow highlighted region is a liquid. And everything under this curve is a vapor. Okay, so if we had different plots on this graph, we can use our knowledge of where each phase lies to determine what that plot's phase is. So if we had plot B here, since it only lies in the solid region, B would be a solid at this temperature here and this pressure here. So let's plot another point. Let's say we have point right here. And let's call this point D. Point D only lies within the blue vapor region, so we can say that it is a vapor at given temp T2 and P2. And lastly, if we had a point here, let's call this E, E would be liquid. So I think you're starting to see and understand how we can use these diagrams. So what if we had points that lied in between two regions. So if they were on the line. So let's call this, so point I, because it's in between solid and vapor on the line, we are going to see both of those states present, solid and vapor. For 2, we see that it is in between solid and liquid. So that means we have solid and liquid present. And finally, for our 3rd region, we have liquid and vapor present. So a couple definitions. We have a point C and A. So let's define what those are. So part A on our graph is an intersection of all 3 lines or phase boundaries. So phase boundaries is another word that we use to describe the curves that separate each of our regions. So these are what we call phase boundaries. So what happens at this section? We have all of our phase boundaries intersecting at the same place. So what do you think this means for our states? This means all 3 states are present at these conditions. Because this point A borders solid, liquid, and vapor. And this is called triple point. Okay, so I'm going to bring up degrees of freedom again. So degrees of freedom was F equals C plus 2 minus P. So if we plug that in, we know it's a pure component, so we have 1 component for this diagram, plus 2, and minus our 3 phases, solid, liquid, and vapor. So that gives us 0. So we can't change any properties. We can't change any properties of triple point. They're all fixed. So triple point is represented by this plot here. So we have our triple point temperature as well as our triple point pressure. Okay, and we also have critical temperature. So this is point C. So this is called critical point, which is a plot of our critical temperature and critical pressure. So everything past this region, so if we were to draw an imaginary dotted line going up from our point C, everything that lies to the right of that region is going to be a different phase. This is going to be our gas phase. Okay, so those are the basics of PT diagrams. The curves that separate our regions are called phase boundary lines. If we have points within a region, they correspond to whatever that region's phase is. And if we have points that lie in between on those phase boundary lines that border 2 regions, then both those regions are present. We know we can only have 3 phases present at our triple point, and anything past our critical point becomes a gas. All right, so I think we already covered what we needed to in that slide. Let's see if I missed anything. Okay, so moving on, we're going to talk about pressure and volume diagrams. So these come from our PT diagrams. So basically it is a different kind of plot or interpretation of it. So some things to identify on our PV diagrams. Each curve here that you see in blue, that I'm outlining in green right now, we call those isotherms. They are called isotherms because iso means same, therm means temperature. So curves all at same temp, right? And it responds to volume versus pressure. And there's different kinds of curves. So with each of our curves, as we connect our lines, we get different phase regions. So where we had phase regions highlighted in our PT diagrams, we have different phase regions here as well. So to highlight this line is our triple line, where we have solid, liquid, and vapor present. Above, we have this envelope here, which is going to be liquid plus vapor present. We have this little region here, and what lies in between those lines is our solid plus liquid region. And on their own, we've got our liquid region to the right, solid region to the left, and vapor to the right of our solid and vapor line. You can also identify our triple point. Sorry, not our triple point, this is our critical point. And anything that is to the right of this line is called a dew point curve, and anything to the left of this line is called our bubble point curve. Right, so this just outlines the regions that we see in these kinds of graphs. I'm going to explain a bit more about how we can get our graphs looking like this from our PT diagrams. So let's define a couple things first. So there are two kinds of processes that we can describe from our PT diagrams. Isobaric process, iso equals same, baric is pressure. So that means same pressure. So in that case, we'd be looking at this set of plots here. So that's C to E, C, D, E. So as temperature is allowed to change, pressure is the same, is constant. So you're going to need to know these terms for questions, because the question might ask you to look at a system that's changing isobarically or isothermally. So isothermally, so an isothermal process means same temperature. So this is plots A to B. And this is the process that we're going to use in order to find our PV diagrams. So use to find PV, and I'll explain why. If we go back up to look at this diagram, we knew that these curves in greens are called isotherms, right? So basically, the process that you see here is like saying going from A to B, right? So the same line that we follow straight up in a PT diagram becomes an isotherm in our PV diagram, because we're isothermally increasing. So used to find PV diagrams. Okay, so this is talking about how we relate the two. So again, you'll see that this isothermal process from A to D is reflected from here. So we are starting from our right and plotting to the left. So I'll kind of walk you through step by step what's going on. Okay, so pressure is common for both of our processes. And let's label this other tick line P0, P0. Then I'm going to draw it across from here. So if we start our P0 at, if we start our plot at P0, right, we know A is in line with it on our PT diagram, and A is in line with it on our PV diagram. And we are starting with a larger volume because at lower pressures, there is going to be more vapor present, right? So think about gas in a container. The larger we make the container, the less pressure the gas is going to be exerting. So at a lower pressure, it occupies more space. So I'm going to write this out. So gas occupies more space at lower pressure. So that's why we are going to want to start much farther on our volume for a vapor, right? Because we know A is all vapor because it lies within the vapor region. Okay, so if we were to go up to B now, B is in line with our, let's use a different color. B is in line with pressure 1 in our PT diagram, and it's in line with pressure 1 in our PV diagram. So as we increase the pressure, so I'm going to write this, as pressure increases, our vapor will condense into liquid. Point B lies on our phase boundary line between liquid and vapor, so that means we have liquid and vapor present. So this slope up to this point from A represents our change in pressure. So as there's more pressure applied to the system, there's going to be less volume responding to it. And there's going to be this region called a tie line when we have two phases present. So when we have two phases present, hold on. Yeah, so this tie line shows that, give me a second. So this shows that a phase change, when phase change occurs, we have constant temperature and constant pressure. Because it takes quite a bit to completely transform all of our vapor into liquid and vice versa. So it is going to take a while. And our length of our tie line is dependent on the steepness of our slope. So the less steep our slope is, the longer our tie line is going to be. So we have two parts. We have our volume of our vapor and our volume of our liquid. And as that pressure is slowly being applied, more liquid is going to, there's going to be more vapor and less liquid specific volumes, if that makes sense. Okay, and lastly, when we go from B to D, call this P2, so if we go up to P2, we are now in our liquid phase. So our liquid phase occupies less volume, so occupies least volume. Occupies less volume at higher pressure. And our change is going to be a lot steeper when going from B to D. And this is because as our phase change is happening, once we reach that final point, so we have just a little tiny bit of vapor left. So if we start from here, we have a lot of vapor, then that vapor is turning into liquid, turning gradually into more liquid, and now we just have a tiny little speck of vapor left. Once we get rid of that final piece of vapor and go fully into liquid, then that change is quite steep and it happens quite quickly. So that's why our line is much steeper. So this is an isothermal process reflected into our PV diagram to create an isotherm. So we can have multiple tie lines. So say if we had a different plot, a different isothermal process in orange right here, that would be reflected by this line, this isotherm here. So it would be at a higher pressure. Hold on. Sorry, no. So since it's at a higher temperature, it's going to be a little higher on our PV diagram. And notice that our tie line is shorter. So tie line is shorter. And that's because as we get higher on our curve, our slope is increasing. So steeper slope on our PT diagram gives a shorter tie line. And if we were to add another process here, that could represent this point, this isotherm here. So as you add more and more isotherms, if you were to connect them together from each of their left side of their tie lines to the right side of their tie lines, this becomes the, let's take a look at our diagram up here. This becomes our liquid plus vapor region. So this whole thing right here, liquid and vapor region. And that makes sense because our tie lines in this process go from vapor to liquid, right? So everything under here, it makes sense that both liquid and vapor are present before it gets fully converted to vapor or before it's fully liquid. Sorry, fully liquid or fully vapor. If we had two phase changes, so this process outlines going from vapor to liquid to solid, that just means we would have another point here. So this part is new. And this encapsulates E and F. So E lies on phase boundary line. So that means we have solid and liquid present. So that means we're going to have another tie line because with phase changes, have tie lines in them. So you see that the tie line is much shorter, and that's because our slope is a lot steeper for this process. And then that will just bring us to our F up here, where F fully represents our solid. So here we have liquid and solid present, and here we have liquid and vapor present in this kind of process. Right, so that just means you're going to have another little bump in the slope. Finally, we're going to talk about lever rule. So we saw on our tie lines that we had two specific volumes. We have V liquid and V vapor. So there's a set of equations that we could use to define the ratio between them. So let's say we have a plot of some unspecified specific volume here. There are three equations that we could use to relate all of these properties together with mass. So relates So if we wanted the mass of how much liquid we had present in this region, so if we want the mass of liquid over our total mass, we would have vapor minus V over V vapor minus our V liquid. If we wanted to find our mass of vapor, we would do V minus V liquid, vapor minus V. And if we wanted a ratio between our mass of our vapor over mass of liquid, this would just be V minus V liquid, V minus vapor minus V. Sorry, I miswrote this one. It's supposed to be V liquid. So this rule is going to make a little more sense. So it's basically just a way to find how much liquid, or vapor is present in a two-phase region. Okay, so that brings us to the end of our review notes. Next, we're going to cover some examples relating to what we just learned with our PV diagrams. It's very rare that on a test that they're going to assess you on PT diagrams. Mainly, they just draw on PT diagrams to help you understand PV diagrams. Okay, so our first example, what is the critical temperature and critical pressure of carbon dioxide? So this is a graph for carbon dioxide. It's a pure substance. So we know from our illustrations above that in our liquid and vapor envelope, so in that loop, at the peak of our loop is our critical temperature and our critical pressure. So that is our critical point. So let's look for the peak of a loop or of that ridge. So in our dotted line, you can see that there's this ridge here. So we follow that dotted line. Watch as it curves down. This is our critical point. So let's draw across for pressure and draw down for temperature. Sorry, no, for volume, not temperature. A is equal to roughly, so let's see, So critical temperature, since our temperature is labeled on our isotherms, we would kind of just find something that's partway in between. So let's just get rid of this clutter. So from our isotherms, we can see that this is roughly in between. So I would say this is in. Sorry, I deviated a little bit. Let's draw this a little better. Okay, here we go. And we see that this touches our 304.19 Kelvin isotherm. So their critical temperature is 304.19 Kelvin. And then if we want our critical pressure, we would read across to where we have pressure in ATM. And that would be about 73. Okay, so that is part A done. Part B. What is our critical density? So I know that density relies on our mass in kilograms and our volume in meters cubed. So let's find out what each. So let's find out our volume. So we read down from our point. I'd say that's about 2.2. So our specific volume is equal to meters cubed over kilogram. Decameters cubed over kilogram in this case equals about 2.2. And let's convert this to our basic SI units. So this is and this is going to give us so 1 cubic decameter is equal to 3 is equal to 1,000 meters cubed. So then this is equal to 2.2 times 1,000, which is 2,200. And we know that 1 over our density rho is equal to specific volume. So therefore, 1 over specific volume is equal to rho. So when we do that, do 1 over V is equal to 1 over, that will be equal to 4.54 times 10 to the negative 4 kilograms per meters cubed. So that's part B done. Sorry, I think I've made a math error for part B. I'm just going to start again. Sorry about that. Okay, so right off our graph, our specific volume is about 2.2 decameters cubed per kilogram. We know that 1 over our specific volume is equal to our density. So this is equal to 1 over 2.2, and that gives kilograms for decameters cubed. 1 divided by 2.2, 0.45. Okay, and next we just need to convert our value. So we have 0.454 kilograms per decameter cubed. And to convert this, 1 decameter cubed per 1,000 meters cubed. Oh, sorry, hold on. Sorry, this is 0.001 meters cubed. And this will then become 454 kilograms per meter squared. Meters cubed, sorry. Unit analysis is very important in these kinds of problems. Okay, what is the vapor pressure of 295 Kelvin? So 295, we need to find where that isotherm is. So we're not given that isotherm on our graph, which means that we will kind of have to estimate where it would be. So let's say our 295 tie line's about right here. And that'd be in between 300 and 290 Kelvin. That makes sense, right? So basically, from this tie line, we just want to see what the pressure is in line with. So then this is about, so vapor pressure at 295 Kelvin is about 60 atm. Does it specify what units we want? So we can just keep it in our atm. Okay, so now we're going to move on to our second part. So if we inject 1 kilogram of CO2 into a vessel with 4 decameters cubed while maintaining a temperature of 280 Kelvin, we allow the system to reach equilibrium. So how many phases are present? All right, so how would we check this out? So what we can do, we can calculate specific volume from our given conditions. So we know that we have volume is equal to 4, and our mass is equal to 1 kilogram. So we can find our specific volume. So specific volume is equal to our volume per our kilogram. So we have 1 kilogram CO2, and that's just going to give us 4 decameters cubed per kilogram. So then let's find that on our graph. So find on graph. Right, so at 4, graphs x-axis for specific volume, and then we're going to read up to our 280 K isotherm. So when we read upwards to 280K, we see that it's on the tie line, so on tie line region. So that means both vapor and liquid and vapor are present. So 2 phases present. All right. So now we want to find the mass of each phase. So this is where our lever rule comes in. So lever rule is to find the mass of different components that are in a 2-phase region using ratios. So that means we're going to want to find what our specific volume for our liquid and specific volume for our vapor are. So to recap, know that on this tie line, our V liquid is at the lower volume, and our V vapor is at the higher volume. So all we need to do to find what those values are is read down. So that's about, so our V liquid is about, say, 0.2, 0.4, it's about 0.5. And our V vapor is roughly about 8.2. Our V is the point that we plotted from our initial settings. So then this is 4. Okay, let's find our mass of our liquid phase. That's equal to So since these are ratios, we don't really necessarily have to worry about units as much. So this is going to be M liquid. And we know our total mass is 1 kilogram because we injected 1 kilogram of our CO2. And that's equal to 8.2 minus 4. And then that is 8.2 minus 0.5. And when we multiply that 1 kilogram over, that's just going to be 1. So that means our mass is going to be equal to, so 8.2 minus 4 divided by 8.2 minus 0.5. That's about 0.545 kilograms of our liquid. For it to do the mass of our vapor, this would be V minus V liquid over V vapor minus V liquid. It's going to give M vapor. And then let's do the same thing. Let's multiply that 1 kilogram over. So then this is 4 minus 0.5. And this is 8.2 minus 0.5. 4 minus 0.5 divided by 8.2 minus 0.5. And this is, and then our mass of vapor is equal to 0.454. And to check, you can add up both of these values to make sure it's equal to 1. Okay, so that is part E done. What is the volume of each phase? Okay, so how would we find that? To solve part F, it's important to know how we got specific volume to start off with. So we know our specific volume. So we know of each phase from our graph. We know the volume of our whole container. And we also know, we know mass. Of each phase. So specific volume we know is meters cubed per kilogram, which is like saying volume over mass. If we wanted to just isolate for volume, volume is equal to specific volume times mass. So if we did that for each phase, so V liquid equals, so V liquid we found to be specific volume liquid is 0.5. And let's convert that while we're here. Actually, for simplicity, let's just keep this in decameters cubed. Okay, and then we need our mass, which we found to be, so this is our mass of our liquid, 0.545. Kilograms. So kilograms are going to cancel out, leaving us with that's 0.272. If we did the same thing for our vapor, that would be, so it's 8.2 per kilogram. We know that's 0.454 kilograms. That's equal to 3.727 dm cubed. And these should add together to give our total volume, which is 4 decameters cubed, which was given at the start of our question right here. Now, what is the mole and mass fraction of each phase? Let's do this in orange. So this is G. So simple enough. Mole fractions are denoted with, so mass fractions are denoted with an X, which is equal to our X total, and then our mass of our total, and mass of our liquid. So then this is just 1 kilogram. We found this to be 0.545 kilograms. So then we are just given 0.545 kilograms for our liquid. For our vapor, so mass of our vapor over total mass, so that's 0.454 kilograms over 1 kilogram, and that's 0.454 kilograms. Oh, sorry, not kilograms, because this is a ratio, so it will not have any units. And then for our mole, for single component diagrams such as this one, we can just use our molar mass equation. So now molar mass is equal to mass per moles. So then that's equal to N equals mass over molar mass. And then we can do this for each one. So we can do mass of our liquid over molar mass of our liquid. Molar mass is the same for both. So CO2 is equal to plus 16 plus 16, 44.01. So then what we can do, we can take 0.545 kilograms in our liquid over 44.01 kilograms per kilomole. And this will give 0.01239 kilomoles. And then for our vapor phase, we'll have 0.454 kilograms. It's going to equal 0.0103. Those are our final answers. In the next video, we will be going over some more examples relating to PV diagrams and how to read them, and how we can use them to find different variables. We're going to continue with lever rule. But this example is a really good question to start with because there's a lot going on at first, but when we apply all the things that we know, it doesn't become that hard. There's a lot of things you have to keep track of, so just make sure your units are consistent and make sure that you are paying attention to your diagram and what things you might need to change about it. All right, thanks for watching.